National Geography Standard Number 7 are the physical processes that shape the patterns of Earth's surface. Take a look at this image, courtesy of NASA, of little bumps in the ground. What are those bumps? Clearly there's a fun pattern there. In this case, it's related to permafrost, or frozen ground. The essence of this standard is that Earth's land surfaces, the atmosphere, the soil, the ground, display a fantastic variety of landscapes, from the Grand Canyon to the Cactus Plains to the Salt River Gorge, including images that you see on the right. This lecture introduces how geography organizes and analyzes and interprets these visual feasts. This course is not a test preparation course to pass the AEPA exam for middle school social studies teachers to become highly qualified. This is a college level course where you learn a lot more information than what you need for passing a middle school social studies proficiency exam. But rest assured that we are trying to clearly articulate what we provide you in information to make sure that you get all of these test objectives covered and more, so you can become a highly qualified, competent teacher where you have a rich background knowledge in the material that you'll be teaching. This particular presentation relates to these test objectives. I suggest that you pause the presentation, look them over, and then perhaps even when you're done with the entire presentation, come back to these objectives and look at what you've learned and how you change your examination of looking at the physical systems from the perspective of these objectives and then the broader college level material presented here. One thing though that's confusing to a lot of individuals, they look at this list and they think this is science, but the course is social studies. What geography is about is linking the different areas of the planet Earth. It's impossible to understand history without understanding the physical system that people lived with. It's impossible to understand cultural geography without understanding the constraints of the physical world. We live on a planet Earth. Natural processes impact our lives all of the time, and so physical geography is a key component to understanding the rest of social studies. The Geography Standard Number 7 is typically organized into 6 general categories of helping you look at the patterns of Earth's surface. We start out by looking at patterns and science. Then look at the 4 spheres or 6 fields of physical geography. Learn to think in terms of different scales, both spatially from the tiny to the big, and in time from the short to the long. Ecoregions is a relatively new tradition in geography, and it's a great way to think about patterns on Earth's surface. There's also a traditional systems approach used in interpreting patterns. So these are the 6 general categories that I'll organize topics in which to help you understand standard number 7. According to Michael Shermer, our brain has evolved to find patterns. It's what we do. You see patterns in everything. People even see the Virgin Mary in a piece of toast. And Michael Shermer calls this tendency to find even meaningful patterns in what are clearly meaningless noise, patternicity. Patternicity and science, well, it's what this standard is all about. TotallyLooksLike.com is a fun website. It really plays on our brain's tendency to identify patterns and look for similarities. Do you see the face in the glacier? Or do you see Godzilla in the clouds above the Grand Canyon? Perhaps there really is an alien skull on Mars instead of just a wind-abraded rock. Or maybe this really is Cheetos, Christ, Super Snack. Can you see Michael Jackson in the Cheetos? My favorite fun pattern in a rock is in the McDowell Mountains, in a place I like to hike, and I think that rock formation looks just like the old Megatron. Don't you? Patterns mean that we recognize patterns either falsely or positively. A false negative is when you don't believe a pattern is real when it actually is real. A false positive is believing that a pattern is real when it's just meaningless noise. According to Michael Shermer, our brains evolved to prefer false positives. Michael Shermer wrote, "If you believe that the rustle in the grass is a dangerous predator when it's just the wind, that's a false positive error. You're more likely to survive than if you believe that the rustle in the grass is just the wind when it's actually a dangerous predator. That's a false negative error." Because the cost of making a false positive error is much less than the cost of being eaten by the predator in making a false negative error, and because there's no time for careful deliberation in our earlier stages of evolution between patternicities in the split-second world of predator-prey interactions, natural selection would have favored those animals and those humans most likely to assume that the patterns are real. Today, we have two choices in analyzing patterns. You can either have faith or you can use science. The choice to have faith that you think the pattern is real, it might be shamanism, paganism, animism, polytheism, monotheisms, or other spiritualisms, such as you believe in ghosts, say, that a pattern that you recognize as a ghost is real or false. Skepticism. Faith cannot be disproved. I believe or I do not. The second choice we have is to use the scientific method to disprove my hypothesis that a pattern is real or it's not. And people who use the scientific method, not just scientists, tend to do this over and over again. You make a hypothesis and you try and disprove it with one type of experiment or one type of observation. And if you run lots of different experiments in lots of different ways, using different techniques, and you still don't disprove that idea that you recognize the pattern, that hypothesis, then scientists tend to call that a theory. It's a way of thinking about a pattern. And the theory can still be disproven with a very different type of experiment, but if it's gone through so many iterations and changes, we bump it up to being a theory. This is the way the scientific method is typically taught from elementary school on, and this is just not the way it really works. A much more realistic view of how science works is that you get an idea. Let's take a look at the Basin and Range Province that stretches from eastern California to Utah. It's a very clear geographical pattern. If you look at the image of the mountain ranges, the topographic image, or the view from the space shuttle looking down at Nevada, you can see that there are a series of north-south trending ranges. So you get an idea on how that might have formed. The most common idea is that the region has been pulled apart and that basins are dropping down. I guess you could think of this as books lined up in a bookshelf where you pull apart the bookends and the books all kind of flop over on their side, one in one direction, one in the other direction, and that results in the appearance that you see of the basins next to the ranges in a whole region called the Basin and Range Province. So you get this idea, you see the pattern, and then you apply a new technology to look at the pattern. You might use seismic waves to look at fault boundaries, or you might measure whether or not the basin is dropping down. You continuously make observation, ask questions, you share ideas, you explore what other people have learned about the basin and range in testing your hypothesis that it's from extension, that this great pattern on Earth's surface is from ripping apart the crusts, pulling it apart. Another example of the reality of science is taking a look at the Mogollon Rim in Arizona. There's an inset map of Arizona where the curved area of green is a higher elevation zone called the Mogollon Rim where there are forests. And the hypothesis is that the greater amount of rainfall on the Mogollon Rim and the cooler temperatures allow you to change the vegetation from desert all the way up towards alpine. So people gather the data, they make this hypothesis, they'll measure the amount of evaporation, the amount of rainfall, the seasonality of the precipitation. Does it occur in summer? Does it occur in winter? And this hypothesis of this very clear geographic pattern is refined to explain why you have forests up on the Mogollon Rim. Another nice example of the patterns and scientific hypotheses is to think about the Phoenix metropolitan area as an urban habitat. You can see the growth of metropolitan Phoenix from 1912 to 1995, and it's continued to grow in the early 21st century. And so as the desert has been swallowed up, there are studies making hypotheses about how desert animals may move into the urban environment. And the cactus wren is an example where people have gone out and noticed that the cactus wren now lives in an urban environment, and it's just making use of the different urban habitats to continue to live. So you start with an observation, and then you begin to explain why the cactus wren has adapted and other birds have not. The idea of this standard is to make observations a part of your daily routine. For example, you can measure and record weather conditions at your home or at a school site and hypothesize about the patterns that you see. For example, the simplest pattern are the diurnal, or the daily temperature changes. If you look at the map on the left, it's a map of temperatures during the day in different parts of metropolitan Phoenix, and then at night. So if you take your daily temperature thermometer, you'll notice that there's a daily pattern where the temperature will peak probably between 3 and 5 in the afternoon, and it'll be the coldest just before dawn when you get up and you get ready to go to school. But there's also your temperature in space or in geography, that if you happen to live or work near the urban core, your nighttime temperatures are going to be warmer than if you work or live in the outside of the urban core. And this is because the thermal radiation bounces around the concrete in the building and keeps the temperature from cooling off too much. Another example of making observations of patterns, a part of your routine, is to look at pollen. The map in the lower right-hand corner is a map of pollen concentrations. And the pollen concentrations are highest in urban areas where people have planted species from home that generate pollen. And so if you look at pollen counts daily and you compare it to wind and the seasons, you can begin to make observations a part of a routine of life. And that's what this standard is about. It's also about looking down. Look where you step. Can you identify the basic earth materials, the basic rock types, whether it's soil or water, and just simply play a game? Is it natural or is it man-made? Take a look at the stones in the lower left-hand corner that somebody did for their driveway. Does that look natural or man-made? Kind of looks natural to me at the surface, but in reality, it's old pieces of concrete that have been broken up, and they're random, and it looks kind of like it's flagstone, but it's reused concrete. Take a look at the lower right. Those river rocks look natural, and they are. They're at the base of Tempe Butte, next to the ASU campus. A lot of students call it A Mountain, and this is on the north side of Tempe Butte. But the setting is totally man-made. There was a drainage ditch where there was a pipe put. So they put the pipe, then there's cement over the surface, and then they put the natural river-rounded rocks of the Salt River on top of it all to give it a natural feel. So it's a combination. Or in the upper right-hand corner, where people use it for kind of an oasis feel, where it's mostly desertified, but there's a feeling of an oasis. Where do those particles come from? In this case, it's granite sand or grus that's been trucked in from a desert site, but those particles of granite sand are natural. I'd like you to pause this presentation. Just hit the pause button and click on the link and watch a video and read about what's going on at an elementary school during a flooding event to nitrogen. Nitrogen is an important element. It's a pollutant sometimes in hydrologic or water systems. And so this is a research project involving students at Arizona State at an elementary school to understand the patterns that happen when you flood in an urban environment. Just watch. Pause. A definite part of the standard is to help you avoid being embarrassed on The Tonight Show. Jay Leno, a longtime host of The Tonight Show, would do embarrassment. Let's focus this. He'd go to college graduates and ask them why there are seasons. I figure it's something that every college graduate should know. Heck, in almost every state, there's a basic science standard and geography standard explaining about Earth's revolution and its rotation and why there are seasons. And the Earth revolves around the sun in 365.25 days, and it rotates in 24 hours, giving you night and day. And the reason for the seasons are not because the Earth is closer or farther away from the sun. That's what most people say. That's actually the opposite. We are closer to the sun in January when it's the northern hemisphere winter. So what causes the seasons? Well, you probably already know, but I'll give you the Cliff Notes version. The Earth's axis is tilted with respect to the plane of the ecliptic, where we revolve around the sun on this plane called the plane of the ecliptic. That tilt causes two things to happen. When it's summertime, in the mid-latitudes especially, you can see this in the graph in the lower left, the sun is higher in the sky, and so the angle of the sun is more intense. Secondly, the length of daylight is longer. So during summertime, if the sun is higher in the sky and the radiation is more intense, and if you get longer sunlight, it's summertime. In the wintertime, the angle is lower and the daylight is shorter. So the net effect is you get much more radiation in summer because of longer days and because of more intense overhead radiation, or it's more overhead. And the winter, the sun angle is lower and the days are shorter, giving you less radiation. It's as simple as that, and now you won't be embarrassed on The Tonight Show. So coming back to patterns and patternicity, at its core, the scientific method doesn't prove. If anybody says science tries to prove, they really don't understand what the scientific method is all about. At its core, the scientific method always tries to disprove a hypothesis. And if you cannot find a way to disprove an idea, it is not science. It's faith. There's nothing wrong with faith. We have two choices to reconcile the patterns that we see. We can choose faith or science. If you choose science, and science is a core part of every bit of the curriculum from kindergarten through college, the key part of the scientific method is coming up with ways to see if you can disprove your pattern recognition. Geography and geographers have a long history of using the scientific method along with other fields of science. And the reason why is the scientific method is the only known method for producing reliable new knowledge. Do you use a cell phone? Do you watch TV? How are the TV images made? How come you can use the cell phone? It works. All of the technology that you rely on is a product of science. In geography, the pattern recognition has been extraordinarily useful. The diagram on the right is a map done by the first epidemiologist or medical geographer. It's Dr. Snow, who mapped out cholera locations in London and connected them to contaminated pump sites. So it's through mapping and through the analysis of patterns Dr. Snow recognized that cholera was connected to contaminated water. That's using the scientific method. You make a hypothesis that's related to water, and you use mapping as a way to test that hypothesis. The second part of this presentation, explaining standard number 7, is about the 4 spheres or 6 fields of physical geography. Traditionally, natural science tends to be broken up into these 4 spheres: the realm of air, the atmosphere; water, the hydrosphere; solid earth, the geosphere; biosphere, the realm of life. And all of these different spheres exist in their other spheres. Even the lithosphere has water and life and air built into it. You can't avoid one in the other. They're not really isolated. Geographers tend to think about these 4 spheres spatially, in terms of space, where any particular location there's the climate and weather impacting that place, the plants and animals, the soils, the geology, the landform shape, and the water. This is the way we tend to, in geography and standard 7, think about those 4. The reason why we organize it this way is it's a good way to understand and analyze the nature of a place. So let me pick on Tempe Butte at the Tempe campus of Arizona State University. Tempe Butte is a mountain. A lot of people call it a mountain because there's a big A on it. And it's a block of rock that's been tilted. The top of the tilt is a volcanic rock called andesite. And the andesite has eroded away on the south side to make a slope filled with these gray rock particles or pieces of broken up volcanic rock. That's on the left-hand side of this image. On the north side of A Mountain, there's tilt, and you can see the geologic material underneath is some layers of sedimentary rock of sandstone or compressed sand and shale or compressed mud. And underneath that are some more volcanic rocks. So what makes Tempe Butte tick? So let's look at the climate of the southern Arizona area of Tempe Butte. One way to look at the climate is to use what's called a climograph, where you display monthly averages in temperature and precipitation. And because we still don't use the metric system, you can see the temperature, average monthly temperature in Fahrenheit, where it peaks in June and July, and it's colder in January and December. Then the precipitation shows up as bars, where in this case the top of the graph is an average of 1 inch in a month, and no months have an average of more than an inch typically. You'll notice the precipitation will peak in 2 seasons. There will be the summertime peak in August when we have the monsoon storms, and then the wintertime peak generally from December through March. That dry, hot climate results in a biogeography of desert plants and animals, like the Gila monster in the upper right, or the creosote bush, that are adapted to severe drought, not having a lot of water. The rock types I explained you can see here. There's the shale and the sandstone in the upper right, and you can see a fault cutting through it. Or there's the general pattern of the tilt of the sedimentary rock shown in the photographs from the lower left, where those 4 black lines show the tilt of the rock. So there's the geology that creates and influences everything else. Soils are very important on Tempe Butte. If you go to the south side of Tempe Butte near Mill Avenue, you'll see a railroad cut. And in the railroad cut, you'll see something that looks like concrete. Actually, it's the buildup of calcium carbonate over time through soil formation. In the diagram in the upper right, you can see the way soils work. Dust, in this case, filters down and settles on Tempe Butte in the A horizon, and what little rainfall there is leaches or dissolves the calcium carbonate in the dust. That's called eluviation. And then the calcium carbonate move deeper into the soil, into what's called the B horizon, and reprecipitate and eventually make that concrete appearance, which is called calcrete. And the calcrete on the south side of Tempe Butte means that the soil is very, very stable. It's very hard to erode, and it impacts everything about Tempe Butte. That dominance of calcium carbonate is the reason why the south side is so stable, and it just is not going to erode. This road cut took probably 500,000 years to form that amount of calcium carbonate. The landforms, or the actual shapes that you see, are a product of all the other factors combined. So for example, on the north side of Tempe Butte, if you look at the photograph in the upper right, and you look at the profile of the slope, you'll notice that down towards the bottom of Tempe Butte, there's a ridge of material, and the arrow is pointing to that ridge, that sticks out a little bit more than everything else. The reason why it sticks out is it's made of a harder rock type. It's made of rhyolite, a volcanic rock that blew out of the Superstition Mountains and cemented together so well that it's harder than everything else. Other things erode faster, and it sticks out like a ridge. Or, on the south side of Tempe Butte, in the middle bottom, you can see a photograph of petroglyphs. And the petroglyphs are etched into a rock outcrop that's a little bit harder. It's stabilized with a black coating called rock varnish, and it created a nice blackboard for these rock engravings. The idea here is that the landforms that you see, the shape of the rock outcrop, the shape of the hill, is a byproduct of everything else going on. Everything affects the landforms, and the landforms affect everything else. The water, or the hydrology effect, can be seen most dramatically on the north side of Tempe Butte, where although right now flooding probably won't occur because the Salt River is constrained by artificial levees built up by the Army Corps of Engineers, in the past Salt River flooding has undermined Tempe Butte on the north side, creating that curve in the parking lot you see by Sun Devil Stadium. There's a flood scene in the 1930s in the lower left-hand corner where current development has been photoshopped on top of where the flooding took place. And in the image on the right-hand side is a flooding that just about reached Sun Devil Stadium itself, where Lot 59 is now at the Tempe campus. So in summary, the nature of a place is a combination of all the different spheres, and it's a combination of all the different factors together that make up a place the way it is. The natural pattern of Tempe Butte exists because it's a synthesis of all these factors. So no matter whether you look at it like a geographer in the upper left, or whether you look at it from the perspective of an ecologist in the middle bottom, it all amounts to this integration, trying to understand the nature of place. The spin of the geographer is that geography, and this particular standard, is focused on the spatial patterns, how Tempe Butte works, why it varies from place to place around Tempe Butte, and why Tempe Butte may be different than the Papago Park area or Camelback. The hope is that you take this perception and you apply it. You analyze this integration of everything in your local setting, and then you add in your own observations. So next time you visit Indian Bend Wash, or the Green Belt in South Scottsdale, between Hayden and Scottsdale, and you might play in a park, you might go play in the lake. What Indian Bend Wash is a natural wash that has been channelized. The Army Corps of Engineers built levees on the side of this green belt to funnel all of the urban runoff through this corridor, because flooding happens quite a lot. If you look at the images up above, you can see that this area floods every time it rains heavily. And the reason why is the hydrograph you see in the lower right. A hydrograph is just a fancy word that means how fast does the flooding occur over time, where the vertical axis is the amount of water moving past a point or a cross section. So let's say the road that you see in the aerial photograph in the lower left, that would be a cross section. How much water is moving past that road in a given period of time? Before there was a city, a lot of the rainfall would sink into the ground and would never make the Indian Bend Wash area. But because the city has put concrete and asphalt down, a lot of the water that hits the concrete runs off through sewer systems and on the surface straight into Indian Bend Wash, and so this hydrograph peaks faster and higher because of urbanization. And so you can go out and you can observe the effects of urbanization on the way water flows and connect that to the other parts of physical geography, to the climate, to the nature of the surface, and how people affect it. Another way to think about the standard is in terms of spatial and temporal scales. I like this diagram on the left, and I'd like you to take a look at it. There's the spatial scale on the vertical, where you go from the globe as a whole all the way down to 2 meters at the microscale. And then there's the horizontal scale, which is the time of an atmospheric effect, from seconds to minutes to days to a week or more. So I've isolated 2 examples here where you can see where they fit. The one on the right is a big, giant cold front, or a low-pressure system that is off the coast of British Columbia, and it's going to be moving into Oregon and Northern California. So it's going to be moving to the lower right, and it's being dragged there by the jet stream. Those storms are called mid-latitude highs and lows, or weather fronts, because there's a cold front and a warm front. And those storm systems are on the scale of 2,000 kilometers across. And they move slowly over periods of days or weeks as you track them across the United States. Or you can look at the other example of a waterspout associated with a hurricane off Florida. It's a waterspout in a thunderstorm, where a thunderstorm has a life of maybe 30 minutes. And the scale of the thunderstorm, the waterspout, might be everything from a few meters across, in the case of the waterspout, to maybe less than, on the order of less than a kilometer for the whole thunderstorm, or you might have several kilometers across for clusters of thunderstorms. So if you think spatially and temporally, and you look at patterns this way, it's what Standard 7 is about. Consider more landform or geological phenomena. The glowing avalanche, or New Ardent of Mount St. Helens, is much smaller in size, but it exists within a global framework, because Mount St. Helens is on the boundary between 2 plates that are converging up in the Pacific Northwest. Or if you think of geologic time as a whole, the 4+ billion years of Earth history, the way geologists look at time, an event of an iceberg calving exists within a small framework of time in the Cenozoic era, which is the last 65 million years. These are big jumps in spatial scale and temporal scales, and it's the way this pattern works. We want you to think about patterns on Earth's surface and how they work in different time scales and space scales. Let's look at ecoregions, which are areas of ecology that link to the hydrology, the soils, and the landforms. There's the macro scale, which is on the order of 100,000 square kilometers. The mesoscale that you might see from the top of a peak when you go hiking. The landscape scale, where it may be between 10 and 1,000 square kilometers. Or the microscale, particular sites that are just a few hectares across, things that you can walk across in a short bit of time. So I want you to think about what happens on the microscale. That as you walk up and over a hill, that the south side of the hill on the right-hand side is hotter because it gets more sun's rays, and the north side can be cooler because it's shaded. So if you look at the patterns and you think about the effect of topography on climate, that's what the standard is about. Or if you look on the scale of a hill slope and you think about the thickness of soil, next time you drive by a road cut where there's a hill, very carefully pull over and look at the thickness of the soil, and you'll notice that up at the top of the hill the soil is thinner, and at the bottom of the hill slope the soil is eroded down and accumulated at the bottom, and it's thicker, and it's probably also has more moisture because the water that has run off of the hill slope is accumulated down low in the thicker soil. So these sorts of microscale observations are useful for helping students understand a site, not global patterns, but something that they can get a handle on. The mesoscale might be something that you can see from an airplane as it's landing or the top of a hill. It's the broader view, but it's still something that you can grasp. You can see the forest and the tree. A fourth general way of thinking about this standard number 7 is to organize it in terms of ecoregions. An ecosystem, the way ecologists think, has everything from the general climate impacting a hill moving down, the topoclimate, or the effect of topography on the climate, the animal and plant life, or the biota, the landform itself, water on the surface, the soils, water in the ground, the rock systems. So the ecoregion is to take those ecosystems and to map them out. You map them out on the macro scale, the mesoscale, and the micro scale. The idea of an ecoregion is something that's fairly new. It's a concept developed by Robert Bailey of the U.S. Forest Service, and it's taken off on a life of its own. It's been adopted by the World Wildlife Federation, by the National Geographic Society, by the U.S. Forest Service, by international agencies. It's a way to think integrated about different biomes, but with a geographical perspective, taking into account all of the 4 spheres and the 6 different parts of physical geography. And if you want to know more about ecoregions, I just suggest you search for ecoregions and Bailey, and you'll come up with all sorts of great material, including online resources for you to learn about different ecoregions. In a general sense, the ecoregions at the macro scale just derive from the temperature and moisture. You have a lot of polar ecoregions where it's extremely cold. You would have the dry ecoregions of the subtropics where it's really dry. And then you would have the humid ecoregions where it's moist and either warm, the humid tropical, or cool, the humid temperate. There are certainly other approaches to map. Köppen's climate classification is a common one, where climates are broken up into tropical, dry, temperate, cold, and polar, but it just doesn't have the power of ecoregions to integrate all aspects of the patterns that you'll see on planet Earth. Another common approach to organize thinking about different biological patterns is by biomes. Biomes are typically mapped out by the vegetation, even though there are animals that come along with the biomes. So take a look at this graph of precipitation versus temperature where the tropical rainforest biome exists. It exists where there's warm temperature year-round with precipitation that there's a lot, but there's a lot of variation. You can have extreme precipitation, 400 centimeters a year, all the way down to 150, and still be called a tropical forest. As opposed to tundra, where it's really cold and dry, you have little precipitation, but it's very cold. It's frozen in terms of the mean annual temperature. So this is one way to organize it, but biomes are not as good as ecoregions because they're not as well connected to the processes that control the geography, the spatial patterns that you see. Ecoregions tend to integrate all of that exists in biomes with the landforms, the soils, the surface water, the groundwater, the geology. It explains a lot more. So try to organize your own observations about what you see with an ecoregions approach. Think about the physical geography system locally. For example, you can go to the Polytechnic campus and observe the ecoregion created at the North Desert Village as a product of everything you see in the diagram. The macroclimate, the topoclimate, the biota that was been planted there, the surface water, the soils, the groundwater, and the bedrock underneath. It's the nature of place, either natural or, in this case, artificially constructed, that is amenable almost everywhere to this type of thinking. A fifth part of this standard number 7 is to think about the patterns you see in terms of a systems approach. And I'll organize and discuss what a systems approach is in terms of 5 aspects of systems. What are they? Boundaries, forces, equilibriums, and thresholds. And system approaches tend to scare people, but they're really simple. So look at this diagram from the Center for Disease Control of food service as a system. Many of you have worked in the food service industry, and there's all different parts that happen to the food service. The systems approach part of this thinking are not the elements in the system. It's not where the reheating occurs, it's not where the service occurs, but it's the arrow. What are the inputs? What are the processes that go on? What are the outputs? And what are the feedback that affects the system? That's thinking about things like a system. The inputs, outputs, processes, and feedbacks. Earth itself is a system, mostly a closed system, where we have those inputs, outputs, feedbacks, and it all better work right. I suppose you can think of a K-12 school or a football as a system. You have inputs of energy. There's the teacher effort, the student effort, the electricity, the PTSA, the custodians, the sunlight, the parent support. You have the input of materials such as copy paper, cafeteria food, the teachers, the students, the backpacks. Then you have your outputs, the learning. Hopefully the students graduate from high school, the salary, reputations, good and bad feelings, and you have subsystems. There might be teams in a school, there's administrations, there might be math department, there's classified staff, aid students. All these have inputs, outputs, feedbacks. Earth as a system has energy input, mostly solar radiation. Earth as a system has occasional things like meteor impacts that generate both energy and material input. Earth is a system, we have a boundary, the top of the atmosphere. Earth is unique in our solar system, not because it has a magnetosphere that protects Earth, because other planets also have a magnetosphere, but it's the combination of that we have a magnetosphere. We have an atmosphere that's breathable. We have a planet with a gravity that's appropriate for life. We have a composition of the atmosphere that is appropriate for life. We have a gravity of the planet that can support the right composition of the atmosphere. There's water in a liquid state that can allow chemical reactions. So the magnetosphere is the outer boundary of Earth that protects us and helps us be a unique biosphere in the solar system. Another aspect of the boundary part of Earth is our position. We're away from gas giants. There's some thought that if the Earth was squeezed between Jupiter and Saturn, it wouldn't exist. In other words, if we had gas giants in the position of Mars and Venus, we would have been ripped apart by gravitational forces. But because we have smaller planets like Mars and Venus, we haven't broken apart. Another way to think about a system is that there are forces in the system. So if you look at patterns on the Earth's surface, in the lower left-hand corner, it's a landform that was shaped by the movement of glacial ice. So the bottom of the ice applied a force, and the force was so much that it polished the rock surface, and that's what you see here are glacial polish and the direction of the ice flow. In the upper right-hand corner, you can see a mountain river, where the big cobbles are on the bed of the river. And look at, on the graph, cobbles and boulders on the graph exist in the far upper right hand corner. And then let's look at the axes. The velocity is in centimeters moved per second. So to erode those cobbles, if you read the graph in terms of the grain size and the velocity, it's about 500 centimeters per second are needed to erode those particles. And then, since they're in a deposited state, if you look at the graph there, they were to be deposited, or sedimentation of particles, on the bed of this river at about 200 to 300 centimeters per second. So getting back to the concept of system, if you have enough force applied from the velocity of the movement of the water, you can erode the particles. If you don't have enough force applied, they deposit, and that creates the pattern that you see here. Either the particles are transported, in which case you can see the river channel, and because they're transported, trees can't grow, and you get the river channel you see here, which is a cleaned out area where water can move through an ecosystem of a spruce forest. The concept of equilibrium is one of balance, and from a physical geography perspective, I think the equilibrium of river systems will help you understand very commonly taught landforms of a delta, a plain, and the mountains. If you think about the change of a river as it moves from the mountains down towards the delta where the river enters the ocean, there is a change in the steepness or the gradient of the river. Up in the mountains, there's steep rivers that have a high gradient, and they transport the coarse gravel and cobbles and boulders that you saw in the previous slide. Then, as the river system gets to be a flatter gradient or a moderate gradient, sand is transported. And when it gets to be very flat and low down by the delta, especially where it reaches the base level of the oceans, there's no gradient, and smaller particles are carried that deposit out and form a delta. The general concept of a river system being very steep in the headwaters in the mountains and slowly grade into a low energy stream down by the delta is called the condition of grade. And that's an equilibrium condition for rivers. That's the condition that rivers like to reach. Equilibrium can be interrupted. You can build a dam and interrupt the equilibrium. You can have a flood and interrupt the equilibrium. But the state of equilibrium is what a lot of systems tend towards. And so if you think about the balances or the equilibrium, it explains the general pattern you see from headwaters to plains to deltas at base level. Another way to think about equilibrium would be the disturbance of an equilibrium. And let's take a hot topic of sea level rise from melting of Antarctic ice sheets. The graph in the lower left is a very dramatic one. It's an extreme prediction. The idea of the people who produced this graph and published it in Science magazine was that the last time the Earth was completely ice-free, didn't have glaciers over Antarctica or Greenland, was a period called the Pliocene, about 4 or 5 million years ago. And during the Pliocene, there's evidence that sea level was between 15 to 35 meters higher. So, if Antarctica melts completely, or giant ice sheets melt, there's predictions of sea level rise on the scale of the Pliocene. And this is when the state of equilibrium of planet Earth would be disturbed in a dramatic sense. I personally don't think that this will ever happen. However, it's something to consider, and it's an example of what happens if the equilibrium is disturbed. The CAP-LTER group at Arizona State University is examining how the change from a desert in metropolitan Phoenix to an urban system has affected the wildlife. Some wildlife have adapted. And what they found, at least their current hypotheses, is that the food chain of the outlying desert ecosystem has been about the same. The herbivores, the plants, and the bird predators are about the same, but a lot of the linkages are different. And the net effect is seen in the lower left diagram is that human activities have altered the predation pressures. There's been more enhancement of arthropods, a reduction for birds. All of the effects you see in this diagram of increased heat island, competition exclusion of the native species, the net effect is just a lower diversity of species in an urban environment. Not everybody's been able to adapt. A threshold can be thought of as pushing something over the edge. Imagine yourself teetering on a balcony on a second floor apartment building overlooking a pool, right? You being on the threshold would be sitting on the edge of the balcony and you're about to go over the edge. It's a scary thought. Please don't do it. But thresholds exist in systems. So if you think about the Mackenzie River in Canada, it gets frozen over in winter, and at some point a threshold is reached where the ice breaks up into sheets, chunks, and pans, and that's a change in the threshold from a frozen system to a system of flowing water. And when that threshold is reached, you get the ice breakup and a lot of hazards that relate. Some other examples of thresholds would be landslides, and including massive debris flow events, as you see in the lower left-hand corner. The map is a map of landslides in the conterminous United States. And where do thresholds come in? Well, if you think about a landslide, I like to think about it in terms of that diagram in the lower right. You get a particle. And when that particle or land moves, it's because of shear stress. Water moving over the surface, water sinking into the surface, that particle is destabilized in landslides. And that landslide, the tendency to landslide, is against the resistance to transport. And the tendency to landslide is enhanced by gravity. So on one side you have the gravity, the steep slope pulling the particle down. You've got the shear stress and the weakening from wetting of the soil on the ground. And then you've got the resistance in the material. At some point, the shear stress and the gravity is going to rip out earth and it's going to move in a landslide or a debris flow, and that's an example of a threshold being reached. Pause this presentation and click on the link to watch a video about a landslide threshold. But before you watch the video, pay attention to that one rock at 5 seconds into the video. You may be able to swing it back and forth. This is what's called a translational landslide that happened in Tennessee. And that one rock moved that altered the balance of the resistance of the material. And that pulling away that one rock was enough to kick over the whole thing into a landslide condition. And it's a fabulous video. The last part of this presentation is the core of geography as a field. Geography is all about linking the physical world, the patterns that you see, to the human world. At its core, geography is about changes to the environment imposed by humans and analyzing them spatially with such tools as geographic information science, things like Google Earth, but much more sophisticated. This is a very scary image about what happens if we disappeared, if our effect on the natural world suddenly disappeared, and it's somebody's plotting of what would happen immediately and over 50,000 years. Immediately, the endangered species would start recovering. Within 100 years, urban streets and buildings would be overgrown. After 50,000 years, we'd just be archaeological remains. It's a turning things backwards. Most people study the effect of people on the landscape presently. This is like what would happen if we disappeared. And there's a entertaining science fiction book written by George Stewart called Earth Abides, about just what would happen if almost the entire human population would be wiped out by disease. And Earth is the main character in the book, and Earth Abides is the name of the book. So let me jump to the micro scale and just give you an example of linkages between the patterns in the physical geography and the human geography. The soil that forms in a tropical forest or tropical savanna is called oxisol. And oxisol is where there's so much rainfall that all of the different elements and minerals dissolve and are leached out away to groundwater, except for the most stable. The iron oxides, Fe2O3, and aluminum oxides, Al2O3, are what remain. And if enough time goes on, you get just a lot of iron and aluminum in the soil. And in India, there's no need to bake bricks. You simply cut up the oxisol soil. You lay it out, and as soon as it's dried, it becomes brick hard because it's composed of mostly iron and aluminum, and you can build houses from it. And the story here is that when people cut down tropical rainforests and the soil dries out, it becomes brick hard, and it's very difficult for a rainforest to reestablish itself on dried brick. Another example of a projected or a hypothesized linkage is the reduction in sea ice in the Arctic. The hypothesis by many scientists is that global warming is occurring, and the effects of global warming will be seen most dramatically and first in the Arctic, where the amount of sea ice is projected to decrease with dramatic changes to the ecoregion. This is a hypothesis, and it's to be tested by ongoing observations. But it's an example of the future linkages potentially between our putting out greenhouse gases and the overall effect on the planet. Maybe it'd be better to think about this closer to home and a more dramatic side. The Vajont River in the Italian Alps is an incredibly amazing example of humans altering the natural landscape. A brilliantly engineered dam was built to block the Vajont River to create a reservoir for hydroelectric power. But the lake rose up to the point where the bottom of a mountain was saturated with water, and it started to move, started to slide. So the engineers freaked and started to drain the lake very quickly. That was a bad move because the lake water was actually supporting the bottom of this giant slide block to be. When they dropped the water in the lake, the bottom of the slide block was so saturated with water that it just started to slide more quickly. The rock slide eventually moved very fast, and the water in the lake was displaced over the dam, creating massive flooding and loss of life. At the micro scale, you can see images on the right of debris flows and mud flows that have flowed out of mountain canyons in the United States, in the western United States, overwhelming houses. So where we build in places where there are natural hazards, or where we create hazards, there are linkages between our activities and the patterns on planet Earth. Thinking about where you live as a system is not that difficult. I think everybody on planet Earth can do it. You can think about where you live in terms of the energy inputs, the material inputs, the boundaries of the system. And if you read this case story about neighborhoods in metropolitan Phoenix viewed as systems, where there's the social and the physical geography context of the residential landscapes where we live, it's a way to think about the interaction between people and place. I encourage you to pause it, this slide, take a look at the diagram, and click on the link and read a short case story. In summary, I love this quote by Meg Urey. Scientists observe nature, then develop theories that describe their observations. Science is driven by nature itself, and nature gives us no choice. It is what it is. Embedded in Meg's quote is the idea of patternicity. We as a species are driven to observe patterns, to make observations, to think about them scientifically. And that's what the standard is all about. This presentation is courtesy of Ron Dorn. I'm the speaker, a professor of geographical sciences and urban planning at Arizona State University. I hope you've enjoyed this explanation of Geography Standard 7.